Right now, 62 million miles from Earth, a spacecraft the size of a refrigerator is crossing the darkness between planets with less than half its fuel remaining. Its mission officially ended 6 years ago. The team that built it watched its sample capsule streak into the Australian desert in December of 2020, and by every reasonable definition, the story should have finished there. But the spacecraft kept flying. And on the evening of July 5th, 2026, it passed just half a mile from an asteroid while traveling more than 11,000 miles per hour. And in the handful of seconds it had, it took a photograph. That photograph shows something strange. Not a single rock. Two of them. Two ancient bodies pressed together into one object, like a snowman drifting through space. Astronomers had suspected for years that this asteroid was elongated. Nobody had ever seen its true shape. Now the image exists, and it raises a question that matters far beyond one distant rock. How do two asteroids become one? And if an object like this were ever headed for Earth, would we know how to stop something that is really two things wearing a single name? This is the story of Hayabusa 2, the asteroid Torifune, and a flyby so fast and so close that the spacecraft had exactly one chance to get it right. To understand how a supposedly finished mission ended up photographing a two-headed asteroid, you have to go back to a launch pad on a small Japanese island 12 years ago. On December 3rd, 2014, an H-2A rocket lifted off from the Tanegashima Space Center in southern Japan, carrying a spacecraft with a modest frame and an ambitious job. Hayabusa 2 weighed about 1,300 pounds, lighter than a small car, and its instructions were straightforward on paper. Fly to a near-Earth asteroid called Ryugu, study it, collect a sample of its surface, bring that sample home. Its predecessor, the original Hayabusa, had attempted something similar a decade earlier and barely survived the journey, limping back to Earth with a few precious specks of asteroid dust after fuel leaks, engine failures, and years of improvisation by its operators. The Japan Aerospace Exploration Agency, JAXA, had learned hard lessons from that mission. Hayabusa 2 carried backups of its backups. Nobody at the launch was talking about the year 2026. The mission plan ran to the end of 2020, and even that felt optimistic. Deep space is not kind to machinery. Radiation degrades electronics. Reaction wheels, the spinning devices that let a spacecraft point itself, wear out and fail. The original Hayabusa lost 3 of them. Expectations for the sequel were high, but the timeline was fixed. 6 years, 1 asteroid, 1 sample, done. For a while, that is exactly how it went. Hayabusa 2 spent 3.5 years spiraling outward on its ion engines, thrusters that use electricity to accelerate xenon gas. The push they produce is about as strong as the weight of a coin resting on your palm, but they can sustain it for months at a time. In June of 2018, the spacecraft arrived at Ryugu, a dark, diamond-shaped asteroid about 3,000 feet across, and what followed became one of the most successful campaigns in the history of planetary exploration. It dropped small hopping rovers onto the surface, the first machines ever to move across an asteroid. It deployed a German-built lander called Mascot. It descended and touched the surface itself, firing a small projectile into the ground and catching the debris that flew up. Then, it did something almost theatrical. It launched a copper impactor into Ryugu at more than 4,000 miles per hour, blasted open an artificial crater, and collected material from beneath the surface, pristine rock that had been shielded from space radiation for billions of years. In December of 2020, a capsule carrying about 5 grams of Ryugu came down under parachute in the Woomera Desert of South Australia. 5 grams sounds small. It is roughly the weight of a sheet of paper. But those grains turned out to be about 4.5 billion years old, older than any rock on Earth, and they contained water-bearing minerals and organic molecules, the chemical ancestors of biology. Laboratories around the world are still analyzing them today. That was the finish line. The mission had succeeded completely. And this is where the story changes. When engineers in Sagamihara looked at their spacecraft after the capsule dropped, they saw something unusual. Hayabusa 2 was healthy. Its instruments worked, its ion engines worked, and critically, its tanks still held a meaningful fraction of their original xenon. Today, less than half remains, but back then there was enough to go somewhere. The spacecraft could never return another sample because the capsule was gone, delivered to Australia. But a functioning deep space probe with fuel in the tank is one of the rarest assets in science, and walking away would have meant abandoning a machine worth well over $100 million while it was still raising its hand. So JAXA gave it a second life. The extended mission had a destination that sounded almost absurd. A near-Earth asteroid designated 1998 KY26, one of the smallest objects ever targeted by any spacecraft, roughly 36 feet across, the size of a house, spinning so fast that its day lasts about 10 minutes. No probe has ever visited anything like it. Getting there would take 11 more years of flying, with the rendezvous set for July of 2031. But the trajectory to that tiny asteroid held a gift, Along the way, the spacecraft's path would carry it near another asteroid entirely, a rock discovered in 2001 and cataloged under an unglamorous string of letters and numbers. The mission team secured a better name. They called it Torifune, after Amy no Torifune, the boat of the gods in Japanese mythology, a divine vessel that carried deities across the sea. A fitting name, given what would eventually be discovered about its shape. Hold that thought. We will come back to it. Torifune is what astronomers call an Apollo asteroid, and that classification means one specific, uncomfortable thing. Its orbit crosses the orbit of Earth. It circles the Sun every 383 days, almost exactly one of our years, and spins once every 5 hours. Ground-based telescopes had measured it at nearly 1,500 feet wide, which puts it in a category worth taking seriously. An object that size striking Earth would not end civilization, but it would devastate a region the size of a country. Torifune itself poses no threat on any timescale that matters, because its path and ours do not intersect dangerously. Its family is another matter. Apollo asteroids are precisely the population that planetary defense programs lose sleep over, and humanity had never examined this one up close. There was a problem, though, and it defined everything about what happened on July 5th. When Hayabusa 2 visited Ryugu, it matched the asteroid's speed and hovered alongside it for a year and a half, descending gently whenever it wanted a closer look. Torifune allowed no such luxury. The geometry of the extended mission's trajectory meant the spacecraft would cross the asteroid's path at a relative speed of 3 miles per second. At that velocity, the entire close encounter, the window in which Torifune would appear as more than a dot, would last seconds. Not minutes, seconds. Imagine trying to photograph a specific pebble on the roadside from a bullet train, except the train is moving 15 times faster than a rifle bullet, and the pebble is the size of a few city blocks, targeted by people working from tens of millions of miles away. And the mission team made a decision that raised the stakes even further. They chose to aim close, extremely close. The plan called for a missed distance of less than half a mile, a figure that made this one of the tightest high-speed asteroid passes ever attempted. One member of the science team openly called it a risky operation, because so much about Torifune remained unknown. Fly too far away, and the images resolve nothing. Fly too close, with an error of a few hundred yards and 11,000 miles per hour, turns a photography session into a collision. There would be no second attempt. The remaining xenon was budgeted, thruster firing by thruster firing, to reach Torifune, and then the final target. Extra maneuvers were not in the ledger. Think about what that means for navigation. From Earth, radio tracking can pin down a spacecraft's position with impressive precision, but the asteroid's own position carried uncertainty, a small, elongated rock known mostly from the flicker of its reflected light. So the team combined two kinds of information. The spacecraft photographed Torifune against the background stars, while ground stations tracked the spacecraft by radio, and merging the two datasets let engineers steadily shrink the error bars on where, exactly, rock and machine would meet. JAXA calls the technique optical radio hybrid navigation. The first direct image came on June 20th, 2026. Torifune appeared as a faint point of light in the spacecraft's telescopic navigation camera. For the next 2 weeks, that camera served double duty, science instrument, and gun sight. Each image tightened the targeting solution. Each small correction burned spent fuel the mission could barely spare, and all of it converged on a single moment that could not be rehearsed, paused, or repeated. In the final hour before closest approach, Hayabusa 2 came alive in a way it had not since Ryugu. The near-infrared spectrometer began reading the sunlight reflecting off Torifune's surface, a way of identifying minerals by their light signature, the same way a prism reveals hidden colors. The thermal infrared imager started mapping the asteroid's heat, which reveals whether a surface is solid rock or loose rubble, because dust and gravel hold warmth differently than boulders do. The LiDAR fired laser pulses toward the approaching rock, timing their reflections to measure the closing distance directly. 4 instruments, 1 accelerating target, and a spacecraft executing the sequence entirely on its own, because at 62 million miles, radio signals take minutes to travel each way, and the encounter would be over before any command from Earth could arrive. One more constraint made the moment truly unforgiving. The observations could continue only until closest approach. The spacecraft could not turn to watch Torifune recede behind it. Everything, the images, the spectra, the thermal maps, the laser ranging, had to happen on the way in and in the instant of passage. Whatever Hayabusa 2 captured in those final seconds would be everything humanity got. On July 5th, 2026, at 6:30 in the evening Japan time, a moment the team would later pin down to within a single second, Hayabusa 2 swept past Torifune at a distance of roughly half a mile. Half a mile at 3 miles per second. The asteroid crossed the spacecraft's sky in less time than it takes to read this sentence. Then, silence. In the control room in Sagamihara, there was nothing to do but wait for physics. The confirmation signal crossed the void, and 5 minutes after the pass, ground stations locked on. The spacecraft was alive, operating normally and carrying data. And then the first image arrived. Ground-based telescopes had told astronomers that Torafune was elongated, a stretched shape, longer than it was wide. That was the accepted picture. The photograph from the navigation camera showed why. Torafune is not one elongated rock. It is two distinct lobes joined at a narrow neck, forming a shape the mission scientists compared to a snowman. The technical term is a contact binary, and this image was the first direct confirmation that Torafune belongs to that family, seen in one of the closest views of such an object ever captured. A contact binary forms through one of the gentlest processes in a violent universe. Two separate asteroids, born from the same shattered parent body or captured into each other's company, orbit a shared center of mass, two rocks slowly waltzing around an invisible point between them. Over immense stretches of time, subtle forces steal energy from that dance. The orbit shrinks, the two bodies spiral inward, closer and closer, until finally they touch. At a relative speed, you could match at a brisk walk. They do not shatter, they simply lean into each other and never separate again. What remains is one object with two heads, fused at the point of contact, holding the shape of an embrace that happened perhaps billions of years ago. If that shape sounds familiar, it should. When NASA's New Horizons probe flew past the distant object Arrokoth beyond Pluto in 2019, it found the same snowman architecture. The original Hayabusa's target, Itokawa, showed a related two-part structure, a body and a head, nicknamed the sea otter. And radar studies suggest contact binaries are common. A meaningful fraction of near-Earth asteroids larger than a few hundred feet may be double-lobed. Torafune's portrait is more than a picture of one strange rock. It is a close-up of an entire class of objects we have mostly known as blurry radar echoes and wobbling points of light. If you're finding this story worth your time, subscribe. This channel covers deep space missions like this one every week. Because what the snowman shape actually implies is where this gets serious. Consider the planetary defense problem. In 2022, NASA's DART mission slammed a spacecraft into the small asteroid Dimorphos and successfully changed its orbit, proof that humanity can, in principle, push a dangerous rock off course. But every deflection calculation depends on the target's structure. A solid monolith responds to an impact one way. A loose rubble pile absorbs the blow differently. And a contact binary is a third case entirely. Two masses, a fragile neck between them, and the genuine possibility that hitting one lobe hard enough could separate the pair, converting a single-tracked hazard into two objects on subtly different paths. Torafune threatens no one, but it is a 1,500-foot Apollo asteroid whose orbit crosses Earth's, and it just taught us that the shape category we most need to understand is real, common, and now photographed at point-blank range. The flyby proved something else, something less about the asteroid and more about us. If a dangerous object were ever discovered on short notice, there might be no time to launch a dedicated mission that gently pulls alongside it over years. The realistic scenario is exactly what Hayabusa 2 just performed. An existing spacecraft, redirected, executing a high-speed pass with seconds of observation time, autonomously, and coming home with usable science. The navigation techniques refined on the approach to Torafune are a rehearsal for the day reconnaissance is not optional. It is no coincidence that JAXA has also partnered with the European Space Agency on missions to watch Apophis, the 1,100-foot asteroid that will pass closer to Earth than our own communication satellites in April of 2029, in front of an audience of billions. And the Torafune data is still arriving. The first images came down within hours, but the spectrometer readings, the thermal maps, and the laser ranging are being transmitted and analyzed now in the weeks after the encounter. Somewhere in those numbers may be answers to the next layer of questions. Are the two lobes made of the same material, siblings from one parent body, or strangers who met in the dark? Is the surface solid or a gravel heap loosely held together? Each answer refines the models for every double-lobed rock in the catalog. Meanwhile, the spacecraft that took the picture never slowed down. It could not. 3 miles per second carried Hayabusa 2 past Torafune and onward along a trajectory that now bends back toward home twice. In December of 2027, it will swing past Earth using our planet's gravity as a slingshot. In June of 2028, it will return and do it again. 2 passes of the world it launched from 13 years earlier, each one flinging it toward the final target, that tiny house-sized asteroid, in July of 2031. An object completing a full rotation every 10 minutes, likely a single solid shard rather than a rubble pile, because nothing loosely bound could spin that fast without flying apart. No spacecraft has ever operated beside anything so small and so violently spinning. By the time Hayabusa 2 arrives, it will be nearly 17 years old, running on the last of its xenon, attempting something with no precedent and no manual. There is a reasonable chance it succeeds. That is the strangest part. This machine was designed for a 6-year mission. It has now flown for 12. It has visited 2 asteroids, landed robots on one, blasted a crater into it, returned the oldest material ever held in human hands, and photographed a 2-headed rock from half a mile away at 11,000 miles per hour, all with hardware built when smartphones still had physical buttons. Still flying, still measuring, still finding things nobody assigned it to find. Somewhere out there tonight, beyond the reach of any telescope that could resolve it, the spacecraft is a spark of engineering crossing a black ocean. Behind it, receding at 3 miles per second, drifts Torafune, 2 ancient bodies that found each other in the emptiness billions of years ago and have been holding on ever since. The boat of the gods, the myth-makers called it, a vessel for crossing the sea between worlds. They named it better than they knew. For a few seconds in July, a boat built by human hands drew alongside it in the dark, raised its instruments like a lantern, and looked. The image is already on Earth. The voyage is not over, and the little ship sails on.